Question D then asks us to estimate the speed of the star relative to the Earth, and we need to state any assumptions. So I've copied and pasted all the important information. We've got the equation that we worked out before, and we've got the three measurements here for the different wavelengths. This one was the wavelength here, the normal source wavelength in the lab. So it's from the lab where they worked out that those are the wavelengths of light emitted in that particular spectrum. And these two up the top are the ranges of wavelengths that were detected from excuse me, wow, from the star. Now something we have to do here, because we don't have excuse me, wow, if only I could get to the pause button quick, then you wouldn't have to endure that. Wow. Let's just say that we've got the speed of light 3 times 10 to the 8, 0.00 times 10 to the 8 meters per second. We're trying to find the velocity of the source, that's our question mark. The wavelength here is our unmodified wavelength from the lab, and the change in wavelength here is the wavelength measured minus the wavelength from the lab. Okay, so the only problem is we've got two wavelengths that are measured from the source. So we're going to have to excuse me, we're going to have to take an average of those, okay, to find roughly the middle. So we'd add those two together, the range, and divide by 2, and then we'd substitute in for into this section above. I'm not going to do the whole thing because you can follow the calculations through, but it's really important just to restate that again. So you find the average of those two, then you substitute that average into here, then you substitute the known value here into there, and that allows us to calculate the change in wavelength. Then we've already got this value, which is over here as well, and we know the speed of light is 3.00 times 10 to the 8 meters per second, so we just rearrange that, and V source equals, you get something like I don't remember, it was 40 kilometers per second or something, 36.7 kilometers per second. Now the assumption that we're making with that, this is a big assumption, is that if this is the Earth here, and this is the star moving away, it's that it's moving directly away, so in a straight line all the way. That it's not, I mean, if it's moving here and moving away, that means it's not moving in a straight line, it's kind of moving at an angle past. Okay, so we're assuming this radial direction is what the answer sheet talks about, so that's what it's talking about when you, so it's definitely, and the further away it gets, if it's up here say and it's moving past, it's going to be a less noticeable effect. So we can work out, in actual fact this should be a minimum velocity, because we're only looking at the radial shift away, which would be a smaller portion of the actual velocity if it's not radial, if you know what I mean. The other thing mentioned in the answers is that relativistic effects can be ignored. That's time dilation and length contraction and stretching and things like that, and that's because both the Earth and the star are moving at significant velocities. So velocities high enough that relativistic effects would would have effects. And relativity is not taught in Year 13 anymore, but you can go and have a look it up, and I intend to put together a few videos on that as well at some point. Okay, let's move on to C. We need to explain two possible mechanisms that cause the emission line from the star to be blurred. So this is the same thing. We have that range of emission from wherever it is up here, 587.60 nanometers to 587.67 nanometers. So you would sort of expect to get a nice constant, same as what you get in the lab. But the lines are blurred. It's not clear. There's a range of wavelength that's detected. So one of the most obvious things you might think about, which is actually wrong, is atmospheric effects. Atmospheric effects won't cause different wavelengths. However, atmospheric effects will bend the light. Okay, it doesn't change when you're talking about scattering, like light coming from the sun and it's scattered. Blue light is scattered the least. That's why we see the sky as blue. Or the most, I can't remember. You can work it out. Here's the Earth, here's the sunlight coming in, and blue light has the shorter wavelength. You work it through. Anyway, that still doesn't change what the wavelength is. Okay, so the wavelength doesn't change because of atmospheric bending, or what they call scattering. Yeah, no, that is right. Red bends the most, and blue bends the least, because let's see, prism, boom, boom, Roy G. Biv. Maybe blue bends the most. There we go. Red bends the least. That's it. Okay, same thing. So that's irrelevant. After all of that, what does affect the wavelength? If you remember that the energy is related or is proportional to the frequency of the light. And so if you change the frequency, or if you change the frequency, you'll change the energy of the light. This is from the photoelectric effect and such. In fact, E equals HF, where H is Planck's constant. So if you were to rewrite this in terms of wavelength, the energy is proportional to 1 over the wavelength. Either way, you change the wavelength, change the energy. So the only way to get different wavelengths is to get different energy levels. And remember, it's coming from electrons that are dropping down energy levels, and as they drop down, the energy they had is given off as photons of light. So you have to somehow change those energy levels, and the only way you can do that is through quite amazing effects. There's thermal motion of emitting atoms. There's talks about stellar rotation. I still don't understand that one. I'll have to have a little look and find out what's going on there. But maybe you could Google these things. So Google stellar rotation, and yeah, I think I've covered all the rest. You can have pressure, you can have electric fields changing these energy levels, you can have anything which could potentially affect the potential energy the electrons have when they're at the top compared to when they're at the bottom. That'll affect the amount of energy that's given off. There we go. I'll see if I can add a few links to some of these other unusual bits for you to explore further.